Hello, my dear warriors. Welcome aboard. Hello, Honey. Hello, Epic Queen. Hello, Jeevi. Hello, Navya. Hello, Roshni, Madhumita. Welcome, Dharun, Ajit Gaming. Nice to see all of you in today's session. The most awaited session with me, Shreyas, your physics master teacher, your captain, your navigator, your guide on the NEET English channel, guys. So I have been, teaching for a very, very long time. I love physics. I almost scored full marks when I wrote my GA exam in the physics paper. And then after that, I joined, a private, electronics and IT company. I left the job and I entered into teaching, and that's how my life story began. And here I am training kids for a very, very long time. I'm so happy and glad that so many of my kids are doing extremely, extremely well. And I hope that you too are going to make me proud, just like these kids have been doing, making me proud for the last 12 plus years. So that's me. And you can also introduce yourself in case you are new to the channel. So today's lecture is all about semiconductors, the class 12th topic, logic gates, electronic devices. So what exactly is going to be the flow? I'll just show it to you. We're going to talk right from the energy bands. We are going to talk about semiconductors types, the N, the and P type, PN junction, and also the reverse and forward bias. We're going to talk about the applications like LED, photodiode, and Zener diode, and also rectifier. Then we'll also go to PN junction diodes applications, and then we'll go to transistor and also logic gates and Boolean algebra. Alright, so that's the flow of today's lecture. Hope you have smashed the like button and also hit the subscribe button. Hello Tiksha, welcome guys. Nice to see all of you out there. Hello Subiksha, I'm very good, very good. So after a long tussle, finally we are here. Yesterday I was supposed to take the class at 9 o'clock, but the board dates are out and I had to announce it on 2 channels and all those mess. So I thought, I'll take the class properly at 7 o'clock today. But again, I went live and some problem happened, so I had to make a new session out there. But good, you guys are here and you get to know whatever updates are there in the Telegram channel, like over here. So if you have not joined the Telegram channel, please join it right over here. Where did it go? Okay, I'm not sure. It should be there. Yes, the Vedantu NEET English Telegram channel. That's the one where you should be, or else you're going to miss a lot of classes. Please make sure that you call up all your friends, ping them, message them, or whatever. Let them know Shreyas sir is live. Okay. So can any attraction occur between south pole and positive charge? Yes, magnetic field can affect charges, but once they are moving. So moving charges get affected by magnetic field, definitely. Hello Prem Kumar, nice to see you. Aishwarya, I'm very good. Nice to see you on this channel too. So let's begin the class, guys. I'm pretty sure you have smashed the like button. In case you haven't, please do that right away. Okay, and subscribe to the channel. Okay, so let's start. Now, what semiconductor is? Okay, if you talk about the crude definition, semiconductor is something which has the conductivity or resistivity or resistance somewhere between the conductors and insulators. So somewhere in between. It's not as conducting as the conductor. It's not as bad as an insulator. Somewhere in between. But these semiconductors have a very unique property, and that is the resistance changes with voltage. Usually, if you have a resistor, basically a conductor, then the resistance is constant no matter how much voltage you apply. But the property of a semiconductor is the resistance varies with voltage. In fact, it is a non-ohmic device. I hope you guys remember Ohm's law. Are you writing this down? It's a non-ohmic device. That means it does not follow Ohm's law. Voltage is not proportional to the current. Alright, so keep this in mind. Okay, so let me just see if this is okay. Is this fine, Prem? I hope the screen brightness and everything is fine now. Okay, great. We are done with nuclear physics, Harshini, last lecture. Okay, now if you have written down all these pointers about semiconductors, so probably I'll just mention it over here itself. So first thing is that semiconductors, okay, if I talk about the resistance of the semiconductor, it is basically more than the resistance of a conductor, but it is less than the resistance of an insulator, or you can take the reverse for conductivity or conduction. Also, they don't obey Ohm's law, so non-ohmic devices. Non-ohmic devices. You can also say voltage decides the resistance, and also these two together decide the current. Okay, so resistance is not constant. That is the important thing. It is not a constant. I hope you have written down all these things, but anyways, you will be getting the PDF later on as well. Now, how does a semiconductor work? What's exactly going to happen? Let's quickly go through the atomic level description and concepts. If you take any element, let's say for example sodium, okay, there are 2 electrons in its first shell, then there are 6 electrons over here, and then there are 2 more, there is 1 more electron in its outermost shell. Correct? Great. Now, if you take such an atom or such an element and you show the energies, remember each electron has different energy. Electrons which are close to the nucleus have low energy, ground state. If you go to higher orbits, higher shells, the energy grows higher and higher. Everybody agrees with it? Non-ohmic means voltage is not proportional to current. Amido, Avogadro, wow, what a name. It is not proportional to the current. That is the meaning of non-ohmic, which does not follow Ohm's law. Okay. The PYQ of atom and duality for J is a different channel, bacha. That will be happening very soon. Don't worry. That will be happening in the next week. Great. So if you look at the energy levels, it looks something like this. 1s, very low energy. 2s, 2 electrons, and then 2p, 6 electrons it has, slightly higher energy. 3s, the highest energy. What are these arrow marks showing? They are showing those electrons in those orbitals. Plus half, minus half. Spins are there. They are forming pairs. Pairs are being formed. Here, Papa, that is single. This is couple. This is single. This is like lone wolf out there. Correct? Now, this is how the energy level looks like for a single atom. But what happens? What happens if you have multiple sodium atoms in a solid? Isolated sodium atom, this is the energy level. What if multiple atoms are there? Each atom, you might think, sir, this will be the energy level of those individual atoms. But actually what happens when they are in a solid? When they are in a solid, then they will interact with each other. What happens? They will interact with each other. Acing, I'm feeling cold, that's why I'm wearing this jacket. So they will interact with each other. And they will form new energy levels. Instead of one line for 1s, there will be, if there are 3 atoms, there will be 3 lines. If there was one atom which had 2s energy level, if there are 3 atoms, there will be 3 lines for the 2s energy level. Because there are 3 atoms interacting, so 3 lines for each orbital have come. Do you see like splitting has happened? Everybody give me a thumbs up if you got this. The atoms interacted, they formed new energy levels because they interacted with each other. Give me a thumbs up quickly in the chat box. Everyone. Yes, very good, GV. Excellent. Come on, guys, mark your attendance. How do I know you guys are here paying attention to Shreyas sir? Excellent. What if there are even more atoms? Okay, you only answer in the chat box. Let's see how smart you are. If there are 20 atoms interacting with each other, how many lines will be there, guys? If 20 atoms are interacting with each other, each of these things will have how many lines? How many lines? Exactly 20 lines. Perfect. Okay. Now, do you see 3p shell? 3p shell, that is empty, right? So it is empty here also. It is empty here, it will be empty here. Electrons can jump, but right now it is empty energy level. So when there are multiple atoms, there will be so many lines. Can you see those lines? Imagine 100 atoms are there. 100 lines will be there. They will be so close to each other, na? They will be so close to each other. If there are so many lines close to each other, can you see them clearly? Na. You will be like, oh, na. I am like, na. Okay, very bad PJ, guys. Anyways, okay, please don't laugh. If you laugh, I will feel that you guys understand my PJ then. Anyways, okay, so if there are so many lines, then it will become so indistinguishable, you cannot distinguish them, that you call it as a band. What do you call? Band. Perfect, Vijay. Perfect, GV. So this is energy band of 1s. This is energy band of 2s. This is energy band of 2p. There will be energy band of 3s. There will be energy band of 3p, and so on and so forth. Very nice. Now, what does this band got to do with anything? What has this band got to do with anything? Yes, it obviously demon corona. Corona in China, corona in India, same row. Same corona. Very good. Excellent. Now, what has these bands got to do? Okay, I'll tell you what. See, those bands which are completely full, like in this case, which were the complete bands? 1s band full, 2s band full, 2p band full. These bands, they are called valence bands. What are they called? Valence bands. But these bands which are empty or partially filled, those are called unfilled bands. They are basically conduction bands. What are these unfilled bands called as? Conduction bands. So all those bands which are not filled are there on the top. All those bands which are filled, they are basically at the bottom. They are called as valence band. Now, what happens is that when you apply your battery, when you connect a battery to such a solid, like you have sodium solid over here, you connect a battery to it. The battery will give voltage, electric field that will pluck those electrons. It will pluck those electrons and it will push them into conduction. If those electrons are in the conduction band, easily they can flow. Conduction, because they are not filled. So atoms, either they are stable when the pairing is formed, or they are completely empty. So these electrons can be easily plucked. If you ask this electron to come out, you'll be like, no, I have a husband or I have a wife, I am not going to come. This, if you ask, hey, come man, let's go out. This has a boyfriend, Pandu Champa. I'll be like, no man, I can't come. Sorry, I have a girlfriend, I can't come. This, hey, come man for party. Oh, it's okay, I'm single only, I'll come. So that's why they are conduction electrons. Understood? Oh? They are conduction electrons, single people. Here the no people only are there. If this electron jumps here, it will be like, what is the use? If I stay here also, I'm single only. Like, I'll just move. So that's what happens in the conduction bands, guys. So now another interesting thing over here is that if the electrons are there in the conduction band, it is going to help in the conduction, but you might have to make the electrons jump from the valence band to the conduction band in case this was empty. Maybe there is no single person. You go and ask, is there anybody for party? Oh, couple here, couple there, Pandu Champa. Nobody is there for me to party. Then deliberately, zabardasti, by force, you pluck out one Pandu, you pluck out one Champa, you pluck out one electron from here, and you push them over there in conduction band. You basically break them up. You break their pairings up. You break them up. You create a breakup over there. That's it, guys. You need some force, you need some energy. So from going from valence band to the conduction band, you need to give some energy. You need to put in some effort. So that effort is given by that band gap. Band gap tells you the minimum energy an electron requires to go from the valence band to the conduction band. Minimum energy required to go from the valence band to the conduction band. Is that clear? Everyone with me on this? So energy levels are discrete, okay, between the highest occupied and the lowest unoccupied levels. Let me just show this to you over here. Highest occupied means this one. This is highest occupied. If you talk about the unoccupied lowest level, that is this one. So the energies are different, they are close to each other, but there is some gap. That band gap is the minimum energy. Now this energy bands and band gaps, etc., are always given to you at 0 Kelvin. This is given to you at 0 Kelvin. 0 Kelvin, lowest, coldest temperature. I'll have to put in 100 jackets if the temperature was 0 Kelvin. What happens when there is temperature? 300 Kelvin, 200 Kelvin, 250 Kelvin, 270 Kelvin. These atoms will vibrate. Dug, 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 dug. They will vibrate. They'll say vibrate, right? And they vibrate. What will happen? When they vibrate, think, imagine what is going to happen. These atoms which are there, they will collide. And who is most vulnerable? Who is most vulnerable? These people. These people, because they are on the outer shell. They might get knocked out. They might get excited to the higher energies. Yes or no? Vulnerable people, outer shells. They are on the periphery. They are on the border. So they are vulnerable. So they will get affected. And because they will get affected, they will get energy because of the collisions, because the temperature is there, vibrations, kinetic energy, rotational energy. They will jump from valence band to conduction band. Yes. The moment valence electron moves to the conduction band, it becomes conducting. It becomes conducting. Great. So it is possible that an element may not have anything over here, at low temperatures, but as the temperature goes up, they will go into the conduction band and they might become conducting in nature. Great. Remember, no electron can stay here or here or here. It's like you stay here or you stay here. You stay here or you stay here. If you stay here, you will fall down. Not allowed. Stay here or stay here. Like it happens, no, from one period to next period. Teacher will tell, okay, sit in this class or sit in that class. Don't roam around in the corridor. So this is that corridor. You cannot. Forbidden. Do you see this? This is forbidden energy. This is forbidden energy. You cannot stay over here. Singles were vulnerable. Even some of the couples were vulnerable, Prem Kumar. Even some of the couples will be vulnerable. What if there is no single? If these doubles only are exposed. Police mama comes, police inspector comes and he is like, come on, out, out, out. Who will get out first? These people. These people are inside. They are deep inside. First, these people will get caught. Okay. Keep this in mind. Okay. Great. Singles so will pakka get caught, but doubles also. Okay. Couples. All right. Great. So now, having said this, what has this got to do with, conductors, semiconductors, or even insulators? Okay. So here is the thing, guys. If this energy difference is very large from valence to conduction, even if you give it thermal energy, even if you shake it, hey, wake up, wake up, wake up, wake up, just like your mom wakes up, wake up, wake up, wake up. No, your band gap, your forbidden zone is so large. From sleeping to awaken, it's a lot of energy. You are like this only. Wake up, wake up, wake up. Nobody is waking up. That's it. You will not go into conduction band. In that case, you are an insulator. Doesn't go. No matter how much energy you give, it doesn't go. Electron only. Push, it will go like this and it will come back. It will go like this, come back. It will go like this, come back. Okay, got it? Very good. If it is semiconductor, you wake up like this. You wake up like this. Okay, what happened? Okay, where? So, little bit of temperature, the electrons jump into the conduction band. So, small conduction is there. Some electrons are there in the conduction band, so conductivity is there. So, that's why semiconductor. Some electrons are reaching. Band gap is typically of the order of 1 to 2 electron volt. Okay, 1 to 2 electron volt. Sometimes, best things can happen here. There is no band gap only. There is no band gap only. Some people, have you seen them? They sleep with their eyes awake in the period. Like this they will be. You don't know whether they are sleeping. And sometimes when they are sleeping, their eyes are open. It is so scary to look at those people. You don't know whether they are sleeping or whether they are awake. Just like virus, you don't know whether it's alive or dead. Same way, if the conduction band overlaps with the valence band, it's like, I can go here also, I can go here also. Oh, I'm dead, oh, I'm alive. Oh, I'm awake, oh, I'm asleep. Very nice. So that is a conductor, guys. That is a conductor. Prem Kumar sleeps with his eyes wide open. Very good, Prem Kumar. That is what conductor is. Understood the difference? Simple, no? No difficulty here. Very good. Excellent. Now, in the semiconductor, what happens? Yes, Sampath Kumar is also demonstrating to us using some emojis. Thank you, Sampath. Sampath, representing emojis, representing conductors using emojis. Very good. I like your talent, guys. So, this over here, this forbidden energy, this band gap from conduction to valence or valence to conduction, it's typically, like I was telling you, somewhere close to 1 electron volt. If the energy gap is 5, 6 electron volt, pakka, gone, it is an insulator. Okay, pakka, it is going to be an insulator. Very, very important things. So this is going to be always at absolute zero temperature. So there is no electron at, absolute zero temperature. But as you give some temperature, so you will see the electrons gain energy and overcome this energy gap, forbidden energy gap, and they enter the conduction zone. That's what a semiconductor is. Very, very important. Now, that we have spoken about semiconductors, okay, which have conductivity between insulators and conductors. There are two types of semiconductors also. Wow, this is crazy. There are two types of semiconductors, huh, sir? Yes, there are. One is called intrinsic, second is called extrinsic. Intrinsic means because of its nature, because of its make, automatically it is its internal property. Intrinsic, internal, because the way it is. Correct? Okay. This one, external, extrinsic. You do something, you poke him. Hey, come on, do something. You also get poked, no? You also get poked, yes. Luxury Hitler, wow, what names, yeah? From where do you get such names? That external factor also can be of two types, P type and N type. The moment you hear this word P and N, what is the first thing that comes to your mind? P, N, charges, positive, negative, exactly what it is. P, like positive, it's not exactly positive, but just keep in mind it's like positive, and N is just like negative. There is some negative element in it, P has some positive element in it. So this is the flow chart, this is the chart which will help you remember the different types of semiconductor. Okay. Now, all the properties of whatever I have talked about semiconductors, I have mentioned it on this slide. This will be available to you in the PDF also. Okay. Yes. Okay. So you will be getting this. All the pointers, whatever I have given. Okay. You can read through it later on. I don't want to go through it now. First, let's have a look at one question which is coming up on your screen. Which of the following is correct? Forbidden energy gap is the gap between valence band and conduction band. I think one or more options might be correct. Are correct? Come on, guys, figure this out. What do you think? So I got it when my newspaper, it torn apart. Oh my God, why was your newspaper torn apart? Forbidden energy gap may be empty or may have partially filled with electrons. No electron can exist in the forbidden energy gap. Bands cannot overlap with each other. What do you think? Okay. A and C says Madhumita. Prem also says A and C. You guys are correct here. Perfecto. Forbidden energy gap is the gap exactly between the valence band and the conduction band. So this gap which is there, that is basically your forbidden. Obviously the electron can either stay here or it can stay here. It cannot lie in between. Correct. It is definitely the forbidden gap. Exactly. Moving on now to the next question. Semiconductor at 0 Kelvin behaves like 0 Kelvin, the lowest, coldest temperature. What does it behave like? Thank you, Archini, for putting that C for Capto. Excelente. Every time you answer C, you should always think of C for Captain Shreyas. Okay, Priya says A. KP Bharat says, Vikram says A. Oh, we have Vikram. We might also have Veda somewhere. Okay. A for Capto. Okay, A for Ames actually. All right, very good. Answer is A, insulator. Correct. Because whatever bands we draw, the conduction band and the valence band, the electrons are here at 0 Kelvin. The electrons reach here at room temperature. At room temperature. Because at 0 Kelvin they are in the valence band, there is nothing in the conduction band. That means it is going to be an insulator. It is going to be an insulator. At room temperature, it becomes a semiconductor. It becomes a semiconductor. Very good. Excellent. Very nice. Perfecto. Now let's talk about both the types of semiconductor. One is intrinsic, internal. Second is extrinsic, which is external. How do these semiconductors exactly behave? What makes it different? So in the purest of the purest form, when nothing adulteration, there is no adulteration. I hope you understand the word adulteration. You have not mixed anything. Like when you get milk, some people put water in it. It is adulterated then, correct? So if you get the purest of the purest form, then it is called intrinsic semiconductor. The best examples of semiconductors like that are silicon and germanium. These are the two most commonly used semiconductors. Now, if you know the atomic structure, you know that there are 4 valence electrons in either germanium, silicon, or even carbon-like atoms. And we know, just like carbon can form 4 bonds, even silicon or even germanium, because they have 4 valence electrons, they can form 4. What kind of bonds are these? Are they covalent or are they ionic? Are these covalent or are they ionic? Come on guys, you know organic chemistry. Definitely they are covalent bonds. Yes, Prem Kumar, just like 24, nice, carat gold. Very good. Now you can see these electrons are getting shared and there can be an infinite chain like that. There can be an infinite chain like that. Like this might form a bond here, that might form a bond here, this might form a bond here, this might form a bond here. A big chain can form of such silicon or germanium atoms. Now when you have such a big structure, of covalent bonds, things can definitely go wrong. Okay, I'll tell you what can go wrong. Okay, observe now carefully. Let me just probably mark it over here only. Imagine that this is one atom, this is one atom, this is one atom, this is one atom, this is an atom, this is an atom, this is an atom, done. So many atoms are there like that. Okay, I'm just showing few of them. Okay, each of them are sharing basically electrons, between them. Now let's say these are all like your neighbors, neighboring aunties. Your auntie, this auntie, that auntie, so many aunties are there in the neighborhood, in the society. They are forming covalent bonds like this. I know I should draw a double line, but just ignore that for now. Each blue line corresponds to sharing 2 electrons. Just visualize it that way. Now just imagine there is friction between them. There is energy, thermal energy. What will happen when there is thermal energy? The bonds will get broken, yes or no? Imagine there is shaking, there is movement, there is kinetic energy, there is rotation, there is twisting. These bonds will get broken, yes or no? Exactly. So at some temperature, maybe this bond just gets broken. The moment the bond gets broken, what happens? 2 aunties fight. It might have happened in your society also. 2 aunties fight. What will they do? Your mom will say, hey, listen, you don't talk to that auntie and her kid. Come here. And that another auntie will say, you listen, you don't talk to that woman, don't talk to that kid over there. Bring this kid over here. That's it. So the 2 kids over here are electrons. Who are these 2 kids? Electrons. Understood? Yes or no? Papa, these 2 kids were playing cricket with each other. These 2 aunties fought because of thermal energy. Gone. These 2 kids are now back to their aunties. Very nice. Now, what will happen? These electrons are now free. Papa, these kids will now start roaming around. This kid will start roaming around. Somewhere else, some other 2 aunties have fought. Maybe these 2 aunties. Now, this kid will start roaming somewhere. This kid or this electron will start roaming somewhere. Understood? Yes or no? Very good. The moment the electron leaves, what has happened is the kid is like, Mommy, why? I don't want to fight. I am leaving the house. Gone. The kid went off. There is a vacancy. The kid left the house. There is a vacancy. That vacancy is called as hole. Vacancy, hole. There is a hole, void left. So the moment that kid has gone, left the place, Okay, so what is left over there is a hole. I'll just put it in a different color maybe. There is a hole created, hole. Okay, so this electron went here, this electron went here. So these green ones are nothing but the holes. Okay, now as these electrons roam around, suddenly maybe this electron which is roaming around like this, it will find a vacancy. It will find a vacancy. What will it do? It will go fill it up. Maybe some other electron roaming around somewhere, some other electron roaming around from somewhere might just fill this hole. It's like your mom found a new cousin. Oh, my kid left me. It's okay, one cousin came. This auntie also found one cousin. Now these two people become friends. These two people become friends, understood? These two people become friends. Crazy, no? Look at the relationship, guys. This is all what is happening in atoms. You thought only you people fight? Look at these atoms fighting like dogs and cats. You go there, I go here, you find a bond, you don't stay with me, I leave you, void is created. So they are fighting like cats and dogs. Bond will be again made over there. So they fill the hole. This is filling the hole. This is also basically filling the hole. And again a bond is formed. Somewhere else a bond is broken, somewhere else a bond is formed. Somewhere bond is broken, somewhere else the bond is made. This is happening continuously. Okay, you cannot stop. So that is what is there in the next diagram. I want you to see it. It might look intimidating initially, but that is exactly the love story, the relationship story which is happening here. You can see bond is broken. Bond is broken. Dotted line means bond is broken. Electrons got free. Vacant electron means hole. You can see vacant electron mean hole. That electron will go somewhere. Electron will go somewhere and fills somewhere else. It will fill the void somewhere else. This void will be filled by some other electron. That void will be filled by some other electron. That electron will go fill somebody else's hole. That's what is going to happen. Okay. Now, when basically all these things are happening, you should also understand holes are created in the valence band. Where are the holes created? I am repeating. Where are the holes created? That's a vacancy in the valence band, because thermal energy has broken the bonds and pushed these electrons into the conduction band. So the free electrons were the ones in pink. The ones, look at this, free electrons. Those free electrons are in the conduction band. From valence band, they jumped into the conduction band. Clear till this point? Okay, very nice. Now, if you understood it till here, let's now go to extrinsic semiconductor. Sir, when is the class of JV? Praveen, I will let you know on the JE channel, bacha. Let's concentrate on this channel now. Okay. Natasha, will. Yeah, I have given you that also. Yes, others. Looks like you were there in the JE channel. Now, this flow of electrons is completely dependent on germanium. But I can create some spicy environment like it happens in reality show. Suddenly there is a new contestant, or suddenly something changes in the serial or in the movie, a new villain or a new hero comes and entire dynamics change. So that is what is going to happen in the next episode. That means now only, don't worry. So we are going to do something externally. We are going to add some impurities. We are going to add some country fellow. We are going to add some villain or some hero who is going to change the entire dynamics of that society. Twist will be there. Now what is the twist? There are two types of things which we can do. P type, positive, you can call it him like the hero, and N type, negative. Okay, you can also call him like the villain. Or you can also think N is like one attractive girl who has entered the society, and P is like one boy who just wants one girlfriend. Okay, P is like one boy who wants a girlfriend, and N is like one very attractive girl in that society. So let's see what is going to happen. Let's start with N type. Are you guys ready? Just light up the chat box. Yeah, ready to see the twist? Ready to see the twist? I'm pretty sure you have not seen semiconductors like this before. You would have seen it in a very boring way, and you would have slept off even before you reach P and N type of semiconductor. Is the number of electrons equal to the number of holes? I'm going to come to that, Sadarshan, but yes, they are. But not in all the cases. Not in all the cases. Okay. Now, what you do what you do is you add N-type material in that big crystal or big compound, or that entire solid. When I say N type of material, that means, look over here, all these were having 4 valencies, 4 valence electrons, 1, 2, 3, 4. What if there was one extra electron here? That is called as pentavalent. So there is one extra electron. This guy will form a bond here, this guy will form a bond here, this guy will form a bond here, this guy will form a bond here. Oh, there is one extra electron. Like, imagine an auntie having 4 kids. One kid, you play with him. One kid, you play there. One kid, you play there. One kid, imagine these days having 4 kids, okay? One kid, you play there. Now 5th kid also comes. This auntie has 5th kid. Extra electron. Now that kid is going to change everything. He will be like, whom do I go play with? These 2 are playing, these 2 are playing, these 2 are playing, these 2 are playing. I will find somebody who has their bonds broken. Oh, their bonds are broken. Zoop, it will go and it will fill up that hole. And not just 1 or 2, but there will be many such pentavalent impurities that will have that extra electron. These electrons will go zoom, find those extra holes, or just find the holes in their neighborhood, and they will go and fill it. The moment they go fill it, that kid will be like, what the hell? You took my place. I just left it, man. Like, sorry boss, I am the new member in this society. I just filled this hole. You do whatever you want. I don't care. Now, Papa, this electron which was staying there, now it will go. It is like musical chairs, guys. Musical chair, everybody has played, no? Like, the chairs are the holes and that extra person is the electron. You will be like, where do I go? Where do I go? No, there is a bond broken. It will go running and fill that up. And that electron will be like, hey, you took my chair, you took my hole, now where do I go? Now it will go searching. So this musical chair will continue. This musical chair will continue. So when you add a pentavalent impurity then to the pure semiconductor crystal, you will see it is called as the N-type because of the extra electron, negative charge. Negative charge. Correcto? Very good. Amazing. So you can see how the dynamics change. Look at this. Extra electron, guys. This is that extra kid. Okay, this is like that extra kid out there. This is going to form a bond. Oh, breakup happened. This N, Natasha, attractive girl, she's going to come here. Like, okay, you can be my boyfriend. Now that guy will be like, okay, I have to find a new girlfriend. That keeps happening over here. Okay. Now if you look at the energy diagram, there is one interesting thing which is going to happen, guys. Look at this, the valence band. We all know there is a hole created in valence band. We know in the conduction band, the electron jumps, right? From the hole, it jumps, right? From the hole, it jumps. When you create N-type, no, this extra electron which is there, this actually comes up over here. This actually, basically, you will see there is one extra electron which is going to be in the conduction band. And you can also think of it this way. That there is one extra energy level, extra conduction level which is created, which basically lowers the gap. Adding this extra electron lowers the conduction energy band to a smaller level, so the gap which was larger will now be reduced. That means it is now easier to make the jump. It is easier to make the transition. So you will see the conductivity will go up significantly. Earlier you had to jump from here to here. That extra electron will create an extra layer of conduction band which will make it easier to jump. Obviously you don't want to jump so much, you just want to jump this much. Exactly. Awesome. I hope this much is clear. Oops, what did I just do? Oh my god, just one second. Okay, I hope it is there. Yes, it is there. Now, I will ask you one simple question, and I have seen this many times, people get this wrong. Is the N-type semiconductor positively charged, negatively charged, or neutral? Answer in the chat box, spam it. Come on. Is the N-type semiconductor positive, negative, or neutral? Quickly answer in the chat box. Bharat says neutral, Prem says negative. What about others? Aishwarya says negative, Hamsini says negative, Harshini also says negative, Vijay says negative, Navya says negative, Dharun, Anger Queen, everybody says negative. Guys, everybody gets negative marks. Most of you get negative marks. I think only one person gets positive marks. That is KP Bharat, Vikram. Very good, Bharat. It is neutral. Mind blown, na? Like, what, sir? I thought, sir, in school they told electron negative charge. What is this you are telling? It is neutral. It is neutral, guys. Why is it neutral? Think carefully. I know this is extra electron, but did you forget that there is an extra positive charge in the nucleus? Understood? See, when germanium was there, 4 electrons are here. There are 4 equivalent positive charge in the nucleus, no? When you have a pentavalent impurity, extra electron is there, but that is extra for the bonds. For the atom, it is neutral. Atom is neutral only because there is an extra positive charge also. Understood, everyone? So it is actually neutral. It's an excess electron for making the bonds. Mind blown, everyone? Very good. But you will see that if you compare the number of electrons versus the holes, because this electron is excess in number. This electron is excess in number as compared to holes, because like musical chair, it's like musical chair, everybody agrees. So you will see the number of electrons is much larger than the number of holes. Number of electrons is larger than number of holes. Holes are like chairs, electrons are like the people. But in case of intrinsic semiconductor, one can say the number of electrons is equal to the number of holes. The concentration is same. It is definitely going to be the same. Keep this in mind. Now, can you guys quickly think for p-type, what will be the case? P-type, what will be the speciality? What will be the speciality of p-type? P positive, one less electron. It's like having more chairs than the people. It's like you have 5 people and you have 7 chairs. These 5 people like, what is this? Is this called a musical chair? It's like the chairs are now fighting for the people. The chair is like, hey, come, please sit on me. That other chair, hey, no, please come sit over me. It's the reverse of the musical chair. Okay, crazy, right? Trivalent, very good. More holes. You can see one extra hole. One, it's like that auntie who has 3 kids. One kid play here, one kid play there, another kid play there. No kid here. That auntie is like, hey, you have a kid, I can send my kid. No kid, sorry. Okay. No kid, vacancy. What will this auntie do? Oh, you come here, you electron, come here, come, play with that kid. Play with that kid. So that electron will come running. There the bond is broken. So the conductivity increases because of the holes. Because of the trivalent impurity. Because of the trivalent impurity. Understood, na? Simple. Very good, very good. Excellent. Awesomeness, guys. Great. Very nice. Now, let's look at the energy levels also. Let's look at the energy levels. So in the p-type, you add trivalent impurities like this. You can see there is one extra hole here. When you create that extra hole, what happens is the valence band energy level goes up. The valence band gets an extra layer of energy. So the band gap reduces not from the top but from the bottom. Remember in n-type what used to happen? The band gap reduced from the top. So this was the gap, it reduced from the top. Here the band gap reduces from the bottom. So the jump becomes easier because of the hole. Where is the hole? Hole is always in the valence band, remember that. So if the hole is in the valence band and extra holes are created, that extra hole creates an extra layer of energy in the valence band, reducing the band gap, creating more conduction. And over here you will see that the number of holes concentration is much larger than the electrons. It's like having more chairs and less number of people, and the chairs are now fighting for the people. Exactly. Oh my God, Harshini, salute. Thank you very much. That is a perfect name for the chapter. It is called Aunties and Kids, Love Story by Shreyas sir. Very good. Now, there are certain formulas which you are supposed to know. There are certain formulas which are supposed to know. So, believe me, these electron and hole concentration are related to each other. They are related to each other. And what is the relationship between them? The relationship is like this. If I have the number of electrons in any semiconductor, intrinsic, extrinsic, whatever, p-type, n-type, you multiply it with the number of holes. You multiply it with the number of holes. Then what you get is the number of electrons or holes in intrinsic semiconductor. If you recollect over here, in the intrinsic semiconductors, Ne is equal to Nh, which is equal to Ni. But if one goes up, the other must go down. If this goes up, this must go down. So what happens over here is that you will get, let me just show this to you. Yes, this will be number of charge carriers in an intrinsic semiconductor whole square. This is the formula. Ne into Nh is Ni square. This is basically the charge concentration in the intrinsic semiconductor. This is the charge concentration in the intrinsic semiconductor. Very, very important. So you can clearly see that if electrons go up, holes goes down. If electrons comes down, holes go up. That's the logic behind this. Last important thing over here before we go to the next part is that the conductivity of a semiconductor is going to happen because of two reasons. You will see electrons going one way and holes coming the other way. Electrons going the one way and holes going the other way, meaning something like this. If there is a hole is nothing but like a positive charge, vacancy, deficiency of a electron. If holes go like this, then you will see that the electrons, the free electrons, go like this inside the conductor, because of which the current will go towards the left side or right side or no current. Come on, answer in the chat box. If holes go like this, electrons go like this, which direction will the current go? Right, left, or not go? Answer in the chat box. I want to see how many of you are going to answer this correctly. Thank you, Vijay. Right side, very good. Positive charge is going that side. If electrons go left, conventional current goes towards the right side. Perfecto, guys. You guys are too good, yeah. Too good. Very good. You guys play along with me. Very good. So the current goes this way. In a normal conductor, tell me, normal conductor, why does the current flow? Because of electrons or because of holes? Or both? In a normal conductor, the flow of current is only because of electrons. Correct? That's what you have studied in current electricity. Electrons flow, that's why electricity flows. But in semiconductor, electrons are flowing only, but holes are also going. That's why the flow happens. Hence, the conductivity of a semiconductor is the conductivity of the holes, plus the conductivity of the electrons, both of the electrons. And the conductivity formula is given by mobility into number of charge carriers per unit volume into the charge. So it will be mu h nh into the charge of the holes, which is E. Okay, what is mu? I'll come to it. Mu is basically called as the mobility, which is nothing but the drift speed upon the electric field below. Okay, upon the electric field below. So that is called as the mobility of the charge carriers. Mu, drift speed, the speed with which the charges move upon how much electric field you apply to cause that motion. That is what it is. Okay. Now over here, what will you put? Mobility of electrons into number of electrons into the charge. So this is the formula for the conductivity of the semiconductor. Very, very crucial, guys. Very, very crucial. And also this is the formula of mobility which you have studied back in the day when you learned current electricity. All these are important things. Okay, everyone? So conduction happens because of electrons also and holes also. Both their conductivities need to be added. Mu is mobility, which is drift speed per field, N is the concentration, and E is the charge of an electron or a proton, which is 1.6 into 10 to the power minus 19. If you want, I'll put that also over here. E is nothing but your 1.6 into 10 to the power minus 19 coulomb. Usually, who will be more, mu h and mu e? Who will be more? If you compare mobility of electrons and mobility of holes, who will be more? Answer in the chat box. Charge with the sign or magnitude? Only with the sign, only with the magnitude. So this is exactly with the magnitude only, don't put sign because it has been already accounted for. Only magnitude. Electron will have higher mobility, correct. Holes are very difficult to move. Electrons can move easily. Vacancies are very difficult to be filled. Holes are very difficult. They shift with great difficulty. Okay, very good guys. Excellent. Now let's go ahead and basically, yes, this was exactly an animation to show you how this works. Just have a look at this animation, the way the electrons are moving. The way the electrons are moving. Look at this. You have applied an voltage. You can see the electrons are going there towards the positive charge. And you can see the vacancies which are created. The vacancies slowly shift from here to here. Vacancy is created here. Slowly that vacancy will shift here somewhere. So the vacancies keep shifting this way. The electrons will keep moving the other way. So this is just a small animation, but I'm pretty sure you have visualized this with aunties and kids. In a pure silicon, which has intrinsic concentration of 10 to the power 16, the crystal at 300 Kelvin, 10 to the power 21 atoms of phosphorus are added per cubic meter, then the whole concentration will be phosphorus. This is pentavalent. This is pentavalent. If it is pentavalent, that means there is an extra electron, hence that will create the electron concentration to exactly 10 to the power 21. Extra electrons are there. Come on. Okay, let's have a look at the formula and use it over here. We know Ne into NH is equal to intrinsic concentrations square. Ne is 10 to the power 21. NH I need to find. Ni is clearly 10 to the power 16 whole square, which is going to be 10 to the power 32. So NH, bring this guy down, so it will be 10 to the power 21. So NH will be nothing but 10 to the power 11. That is the final answer. 10 to the power 11. Very nice. That's the correct one. Option C. Okay. Anant, learn the transistors today. I know transistors you are getting scared, but I'm going to teach you transistors also today. Okay, don't worry. Attend this class. Guys, I'm telling you, 4 marks in your pocket because you are going to attend my 2.5 hour class today. I don't know, it might be more. Hopefully, we'll try to complete as much as possible. Let's go now to PN junction. What is this PN junction? P type, N type. Interesting. Imagine one society where there are aunties which have 3 kids mainly. Okay, few aunties have 4 kids, but some aunties have 3 kids. Neighboring society, there are aunties with 1 extra kids, matlab 5 kids. Many aunties are there with 5 kids, some aunties are there with 4 kids. Imagine both these societies are next to each other. Tell me guys, what is cooking in your mind now? There is one society where each house, each auntie has 4 kids or 5 kids. Another society where each auntie has 4 kids or 3 kids. One society more kids, one society less kids. This society, these aunties need kids to play around. Basically, holes are there, that means P type. And the other side, N type, that means more electrons are there. They are looking for holes. Electrons are going to jump onto the holes, right? Correct? Electrons are going to jump, right? Immediately Aunties call the extra electron, aunties will be happy. Yes, you will be like, sir, it is a win-win situation. But that is what creates the problem. Like, sir, can't all the kids go, sir? Can't all the kids go and, play, and they can form bonds, they can make friends? That is what you are thinking, but something else is in store. There is a twist, guys. So p-n junction is formed by placing, p-type and n-type close to each other. So one side you dope it with p-type, that is trivalent. The other side you dope it with n-type, that is pentavalent impurities. You can see p-type has many holes as compared to electrons. Hole concentration is more as compared to electron concentration. In n-type, the electron concentration is more as compared to the holes type. Now you can obviously guess the electrons are going to immediately jump from here to here. That's what is going to happen, but that itself creates a problem. See what is going to happen now. Okay, oops, yes, over here. Now I'm going to show this to you. There is going to be a very good war fight which is going to happen, and I want you to see this. So this is n-type, this is p-type. Okay, n-type, p-type. Everybody with me? The moment these electrons jump, these electrons try to go and basically form bonds, make new friends over here. There comes a problem. I had told you p-type and n-type are neutral. There is no net charge, neutral, correct? But the moment the n-type loses the electron, what will be the charge on the n-type? Answer in the chat box. Prem, exactly opposite. N will become positive because electrons are leaving. Electrons are jumping over here. So P will become what? Negative. Crazy this is. Exactly. So in the next step, I'll just show the charges being formed. I'll just show the charges being formed. Look at this, huh? So there is basically P will become negative, right? So basically there is negative charge over here and there is positive charge over here. So where will the electric field be? From positive to negative. Electric field will be like this. This is the direction of electric field. So if there is now another electron which wants to make a jump into this hole, think which direction will the force on that electron be? If the electron wants to go here, electric field is here, the force on the electron, which direction will it be? Answer in the chat box quickly. Left side or right side? It's a negative charge. So force is opposite to the field. If it was a positive charge, it is in the direction of the field. Exactly, my dear students. There will be a force like this. This is the force on the electron. Oh, that's bad. Papa, this electron wants to jump over here. But you know, such evil kids are there. These kids jump, no? But they are saying, hey, I found my friend, but I am not going to allow you to come here. But that guy is like, Papa, listen man, there is a hole. This guy wants a friend. These electrons are like, we made a field. We have created a field of ourselves and we will not allow you to jump over us. Papa, so many electrons are waiting there. So many holes are waiting here. They want to jump, but this force will stop them. This becomes like a barrier. This becomes like a barrier over there. So there is a very nice barrier which is created. In fact, I can also say, because the field always goes from high voltage to low voltage. High voltage to low voltage. So this side is at higher voltage. This side is at lower voltage. If there is high voltage and low voltage, what is created? There is a potential difference. Potential difference which is called as the potential barrier. There is a potential barrier which is created. Electric field creates potential barrier because these kids are not allowing them to climb to the other side. There's a barrier. That is also called as a potential barrier or barrier potential, whatever you want to call it. This zone where the barrier is created, it's like no man's land. No man's land, it's like border. People going back and forth. Okay, anybody comes, shoot him. Anybody comes, shoot him. That's it. Nobody can come over here. So this is no man's land. That is why it is called depletion zone. No man's land. This is also basically your depletion. What is it called? Depletion zone. Understood, everyone? Very good. Now, because the electrons initially they jumped from here to here, where is the direction of the current, my dear students? Because the electrons are jumping from here to here, current will go like this. The current will go like this. This process of the electrons jumping from here to here, this process is basically called as diffusion. What is this called? Diffuse. The moment these electrons see, oh, there are holes, they'll go running like this. That is called diffusion. They diffuse. That is why this current is called as the diffusion current. What is it called? Diffusion current. Very good. Excellent. So you can see, don't worry so much about the diagram. This is just an animation to show you, like how the electrons basically jump from one side to the other side. So you can see N-type has a lot of electrons. These electrons are slowly going to go to the other side, P side. From N side to P side, they are slowly moving. So the moment they go, they will satisfy the holes, but they will create a barrier. They will create like a barrier. Electric field will create like a barrier which will prevent the further flow of electrons. That's what happens. Okay. So the diffusion current is created when the electrons diffuse from the N side to P side. N side becomes positive, P side becomes negative. The diffusion current is from P side to the N side. Very, very important. Okay, keep this in mind. The diffusion current, because the electrons go from N to P, current is the flow of positive charges. So it will be towards N side, from P towards N. Okay, everybody should be knowing this. So difference in the concentration diffuses. So you can see the motion of charges gives rise to diffusion current across the junction from P side, from P to N. Keep this in mind. Very nice. Okay, now there is another problem which is going to happen, and that is called as drift current. Okay, so I'll tell you what exactly happens over here. So this is our junction. This is our junction. Okay, this side was P side, this side was N side. We saw that on the P side there was negative charges which was created because the electrons jumped, and over here from the N side there was holes, or I can say positive or vacancies created, we can say, because the electrons are left. Now we also saw that there was electric field like this. This was your electric field. In this depletion zone, okay, in this depletion zone, there will be some kind of fighting. There are many aunties here also, okay. This is at microscopic level. There are many germanium atoms, silicon atoms over here also. There will be fighting which is going to happen here also. So some point of time, due to the thermal energies, because of the collisions, because of the twists, bonds will be broken. The moment a bond is broken, what will you see? You will probably see a free electron, and probably you might see a hole. So this electron hole pair will be formed. What is this? Looks like a traffic signal. What is this? This is electron hole pair which is formed. Where is it formed? In the depletion zone. Everybody fine till this point? The moment this is formed, everything goes haywire. Where will the force be applied by the electric field? This electron will be obviously pushed here. So the force on the electron will be this side, but the force on the hole, because it is like a positive charge, it will be this side. So guys, think and tell me, if electron is going here, hole is going here, which side is the current flowing? Negative charge is going there, positive charge is going here. Which side is the current flowing? Obviously this side, because of the positive charge it will go here. Negative charge going there, current is going here. Perfect. So there will be a current which will flow from there to here. This phenomena is called as drifting. This is called as drifting, and this is called as the drift current. What is it called? Drift current. Exactly. Now, is the direction of drift current same as the direction of the diffusion current? Let's have a look. Where was our diffusion current? Diffusion current was this side, from P to N, but drift current, look at this. Drift current is exactly opposite. Diffusion is this way, drift is that way. Both are opposite each other. What will they do? Okay, I know there is some text over here. I'll shift this diagram later on, or maybe if I can shift it now. What will they do, guys? Okay, meanwhile answer it in the chat box. What will they do? Oh, I can't shift it now. Okay, okay. I'll shift it later on. Okay. So KP Bharat, what happened is basically, observe this. See, electrons will be formed even inside this depletion zone, electron holes. That process is there every time. It will be done here also, here also, here also. The moment electron and holes are formed, what will happen? Because there is an electric field, that electric field will apply force. So it will force the electrons there, force the holes here. So because of which the current will be towards this side. Because electrons are going there, current is this side. This phenomena where the electron holes are formed inside the depletion zone, that is called drifting. That's why this current is called as the drift current. So the net current will be zero. They'll cancel each other. Correct. So you will see, usually in a PN junction, N type, you will see the electrons jumping from the P type. But in this depletion zone, these electrons will be jumping back from here to here. From N side, they will be jumping over here to the P side. Simultaneously, an equilibrium from the P side, or there will be some electrons where the pairs are formed, you will see that they will be jumping towards this side. So an equilibrium is achieved, so the net current will be zero. Understood? Exactly. This is called as unbiased. Very crucial, guys. So in an unbiased, do you know the meaning of unbiased? Unbiased? Like some teachers are there, they are biased. That kid, no, he always says good morning to me in the corridor. I'm going to give him +1 mark in the composition. That kid, very naughty, always keeps smiling. He doesn't deserve so many marks. -1, I'll not give 5 marks, I'll give 4 marks. That is called bias. You're partial. Unbiased means, it's okay, whatever he does, he does. He has written so much, I'm going to give him that much marks. That's all. Okay. So in an unbiased, why is this unbiased? Because you have not done any partiality. You have just left P type and N type to be as it is. You have not said, hey, no, electrons, listen, you go there. Hey, listen, you come here. You have not done anything. You have just left them to themselves. So that's why it's unbiased. So in an unbiased PN junction, you will see that the diffusion current will be equal to the drift current, and because of that, they will cancel each other, and because of that, the net current is going to be zero. Very crucial stuff. Very nice. Don't worry, I will move this later on, okay, on the next slide or something. Don't worry about it, okay? You will get that clearly. Let's see, which current does not depend on minority charge carriers? Most are biased. Okay, thank you for letting me know. Even I felt the same when I was a kid, no? I was on the worst part of biased. Yes, definitely, Gogsdar. Definitely. If I follow, can I completely do full revision? So Gogsdar, I won't be able to do full syllabus before 24th, but I'll be doing all the important topics. Okay? Okay. No, I said I was a victim. Like when I was a student, that time teachers were biased towards me. Not on the better side, for the bad things, because I used to be very mischievous. I used to always get called. My parents were always like, see, your kid was laughing, see, he was not attending the class, see, he was throwing, he was hitting somebody, all these things. Okay, anyways, the correct answer is drift, which current does depend on the minority charge carriers. That is drift. Yes, which current does depend on the minority charge carriers, because that is on the very few number of charges which are created inside the depletion zone. See, in this depletion zone, bichara, these are small number of charges which are created, not like diffusion, which happens because of the majority charge carriers. Now let's talk about biasing. Bias means everybody knows you are creating partiality. Now you tell, hey, listen, P type, I will give you higher potential. Hey, listen, N type, I'll give you lower potential. Biased. Or reverse, P type, listen, I'll give you lower potential, N type, I'll give you higher potential. How do you create potential difference? By connecting a battery. This is the bias. You connect one terminal of the battery to one side, other terminal of the battery to the other side. That is creating a bias. Okay, Bharani, like I have put up on the pinned message also, this is going to take quite some time. It's a very long chapter, so stay tuned with me. Because of the bias, you will see what will happen is that depending on how you connect it, current will be either higher or it will be lower. Now you guys only think and tell me that if the higher potential or positive plate of the battery is connected to the P type, negative terminal is connected to the N type, what will the battery do? Battery will be like negative, repel. See, it's pushing. Push those electrons, tuck, karke. It is forcing. Hey, you go, man, go, karke. This positive, what is this positive doing? Think about it. This positive will pull the electrons. Now, did I not tell you, from N side to P side, the electrons jump. Now, those electrons which jump here, what will happen? They will get pulled by the P type, the positive terminal of the battery. Yes or no? From N type, when the electrons jump over here, the electrons will get pulled by the positive plate of the battery. And similarly, when these electrons jump here, there is some vacancy created here. That vacancy is being fueled by the negative plate. The negative plate will give the negative charges. So that's a good thing. That is helping the current. But there is a problem in that. See, just because you connected positive negative does not mean the electrons will be happy to go here. Remember, there is a barrier created here. Remember, those kids were there. They're like, no, you cannot cross this depletion zone. So you need to increase the voltage a little bit. Then also this barrier will be strong. It will become weak. It's like a fortress. It's like a wall of people. They're like, no, we are not going to allow you. We are not going to allow you to cross over us. Then when you apply little bit more voltage, the barrier voltage is broken. The barrier potential difference is broken. The barrier is gone. The depletion zone completely vanishes. That's it. Poof. You will see all these electrons can freely flow. There is no barrier. There is no border. Can freely flow. So sudden shoot up of the current. So the bias should be such that it is able to overcome the barrier voltage. Then you will see the conduction increasing significantly. That's forward bias for you. So when the biasing voltage is increased, the barrier voltage decreases and the width of the junction, or basically the depletion zone, also decreases. And finally, they overcome and cross over to the other side. So something like this, when you apply forward bias, I think the animation will show you. The electrons were going here, they are filling the holes from N side to P side. Now they can easily go to the other side. Tuck, 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 tuck. The voltage difference has been reduced. You have made sure that there is negligible barrier over here and it is easily able to fall over to the other side. That's what it does. Now in reverse bias, exactly opposite, guys. See what is happening. You are connecting the negative plate to the P type, the positive terminal to the N type. It's like saying, if the electrons which have jumped from n type to p type, do you see these electrons have jumped from n to p? Okay, these electrons are not pulled by the positive plate. In fact, they are repelled. There is a negative terminal here. This is saying, hey, you stay there. Stay there. Keep quiet. Don't come here. And there is a positive charge here because from n to p there were electrons jumping. This positive is being pulled by this positive. Sorry, not pulled, pushed. Like, listen, you don't come here. In fact, I'm going to push you. You stay there. You don't come here. So this negative plate is pushing these electrons here. This positive terminal of the battery is saying, listen, you stay here. No current. Hardly some current will flow over here. Hardly some current will flow. In fact, you are adding to more troubles. You are saying, okay, let the negative charges accumulate here. You are increasing the fortress. You are increasing the depletion zone. The positive charges will go over here. It will add to the width of the depletion layer. The depletion layer actually increases in size. So in the reverse bias, you see hardly any current will flow. Hardly any current will flow. Very few negative charges will jump over here and they will go like this. They will hardly, because this negative is repelling, is forcing these electrons to jump over here. It's forcing these electrons to jump over here and go like this. Because the electrons go like this clockwise, current will go that way. It's a very, very small amount of current. So finally to conclude, in the forward bias, the net current which is there is because of the diffusion minus the drift, but this drift is negligible, is generally negligible. Okay, so diffusion current is higher than the drift current. So you can see the diffusion, I diffuse, will be higher than the drift current. So that's why you will get the net current in that direction. I know electrons are going like this, but flow of current will be, conventional current will be like that. Okay. But in the reverse bias, you are going to see that the drift current will be like this. The diffusion current will be small. The diffusion current will be small. So the net current will be the drift current, which is higher, minus the diffusion current, but usually the drift current only is so small. If you subtract the diffusion also, that's it. This is negligible totally. Negligible in total. The net current itself is very, very small. Okay? Everybody with me on this? Everybody has understood till here? Everybody with me? Great. So how does the graph look like when you plot it for different voltages for different currents? This is the graph. Observe carefully. Forget this part. First look at this part. This is forward voltage. This is the current. You can see as you increase the voltage, there is hardly any current, forward bias. But suddenly there is a shoot up. Why there is a shoot up? By the way, that is also called as knee voltage. That is also called as the knee voltage. Why is there a shoot up? Because here you are overcoming the barrier voltage. You are overcoming the resistance, and then once that barrier is destroyed, that depletion zone is destroyed, free flow of electrons will happen. Electrons will flow freely. So that is what knee voltage is. After that, the current shoots up. Also, do you see voltage is not proportional to current? Voltage not proportional to the current. Do you see that? So therefore, is the resistance constant? Definitely not. No, voltage is not proportional to the current. It is definitely not going to be following Ohm's law, nor is the resistance constant. If you want to find the resistance at any point, just find the current, also find the voltage at that point. So the value of the resistance will be nothing but, because V is equal to IR, R will be nothing but voltage by I, which will not be a constant at any given point. It will be a non-ohmic device. If you go the reverse way, observe what is happening. Observe what is happening. Very, very small current is there. That's why it is called leakage. Why is it called leakage? Because this current in the reverse bias is very teeny meeny because of the drift current. So that is why it is called as the leakage current. It is hardly noticeable. This is crazy. If you connect the PN junction in forward bias, it gives good current. If you connect the PN junction in reverse bias, hardly any current is there until you give so much voltage that it breaks down. It's like, okay, just, it's okay, man. Let's just flow. So there is a sudden surge in the current, but that is after breakdown. That happens after a long time. After a lot of voltage, it breaks down. It finally is like give up. Okay, please don't think that, sir, this point and this point are identical. No, it's not symmetric. This is not a symmetric graph. This knee voltage is 0.3 volts, 0.4 volts, 0.5 volts. This breakdown voltage can be 10 volts, 5 volts, 20 volts, like that. So be careful about it. Okay. So my dear students, the reverse voltage current is very, very small. It's called as a leakage current. The breakdown happens after a large amount of reverse voltage, and you will see that the resistance in either of the cases is not going to be constant. That's why this graph, by the way, is also called as the voltage current characteristic graph. You tell me the voltage, I'll tell you the current. You tell me the voltage, I'll tell you the current. That's how this graph tells me how things are going to be affected by the voltage. You can also see only in the forward bias, the current flows significantly. In the reverse bias, hardly any current flows. It's like a valve, I feel. It's like a valve, I feel. Have you seen walls? Do you know where are the walls in your day-to-day life? Have you seen walls? V-A-L-V-E. Walls. Yes, no, come on, put it up in the chat box. Do you know where are the walls used? Tap, okay, great. What if I tell you it's there in your human body only? In digestive system, yes. In your arteries, near the heart, is it there? Is there some kind of a wall? Is there some kind of a wall? Yes, to prevent black flow. Very nice, arteries and veins, perfect, perfect. Look at you guys, biology students, you will definitely know it. So what is the function of a wall? It allows the flow in one direction, prevents the flow in the other direction. Are you getting the same feeling looking at this particular graph? It allows the current in one direction. In the other direction, it's like leaking, hardly anything. Yes? No? So that device which allows the flow, not of blood or of food, but of current in one direction, is called as a diode. Diode is a device which allows the flow of current in one direction. In the other direction, it's like one way. Sorry, traffic police is there. No, 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 no entry. Go back, turn back. That is what a diode is. Now, how did you make this diode? Using what did you make this diode? If you forgot, let me remind you. What did you make this device which allows the current only to flow in one direction? Using P and N junction. So that is why it is called as a PN junction diode. What is it called? PN junction diode. Understood the nomenclature, where this name came from? Very nice. How does it look like? It looks like this. It's very small. It's probably the size of your fingertip. That's small it is. It's very, very small. Okay, this is a zoomed in image of a diode. Inside that there is a semiconductor P side, N side, and these are the two terminals of that diode. It allows the flow of current only in one direction. So this is the symbol. This is what is there inside of it. This is the actual photograph. The symbol of a diode is a triangle. Now the triangle points in the one direction. That is the direction in which the current is allowed. If the current goes this way, it will be opposed. So this is allowed. This is like one way. This is not allowed. That is the meaning of the triangle. Cool? Everyone with me? Great. Let's see if you guys can solve this. The current voltage characteristics of a PN junction diode is shown. Approximate resistance of the PN junction. Oh, I forgot to tell you about dynamic resistance also. 1 second guys, let me just tell you over here. This resistance over here, usually which you find, that resistance is just called as the static resistance. This is just called as the static resistance. But there is one more thing which you should know. If this is voltage current graph, okay, and if you measure voltage and current at some point, and then at some other point you measure the voltage and current, let's say this is the difference of the voltage, let us say this is the difference of the current, then instead of V by I, if you measure delta V by delta I, that is called as the dynamic resistance. Dynamic resistance, very, very important. Usually when we calculate resistance, we usually calculate static resistance. This change in the voltage per change in the current, that is called dynamic because it's the change. This is static. At that voltage, this is the current, static. Change in the voltage, change in the current ratio, that's dynamic. Okay, very important. Great. Let's try to solve one question on this. The current voltage characteristic of a PN junction diode is as shown. This is voltage graph. This is current in milliamperes. The question is, what is the approximate dynamic resistance of the diode when in the forward bias as shown when 2 volts is applied? Yeah, it's like instantaneous and average. Yes, you can think of it like that. Okay, come on my dear students, what do you think about this question? Dynamic resistance. Dynamic resistance is basically delta V by delta I. Difference of the voltage, you can see it is 2.1 minus 2. Difference of the current is 800 minus 400. But careful, this is milliampere, so 10 to the power minus 3. So this is just going to be 0.1. This is going to be 400 into 10 to the power minus 3. So this is going to be 0.1. And you can see this will just become 0.4, correct? Because 2 zeros goes and one more decimal. So this is 1 by 4. That's it. 1 by 4 is nothing but 0.25 ohms. 0.25 ohms. Very nice. That's the correct answer. Very good. Excellent. Understood. These kind of simple problems also come. Let's move on now. Of the diodes shown in the following diagrams, which one is reverse bias? Come on, this is a tricky one, logical one. You will have fun solving this. Diode, voltage, voltage. Diode, ground. Ground means 0 volts, voltage. Ground means 0 volts and voltage. Voltage, voltage, diode. Look at the direction in which the diodes are connected. One of these diagrams is reverse bias. Figure that out, guys. Which is reverse bias? Which is reverse bias? Both B and D? No, not B, not D, it's C. Let's understand why. Some of you got it, perfect. Let's see. Hey guys, this is -5, this is -12. Okay, so if you mark the points, this is at -5, this is at -12. This is lower, right? This is basically higher, right? This is P, this is N. P, N, that's what the symbol is. In the diode, that base of the triangle is P, the pointing arrow mark is towards the N type. Positive and negative, P, N. This is at higher, this is at lower. This is definitely forward bias. This is definitely going to allow the current to flow in this direction. Got it? Perfect. Similarly, look over here, this is 0 volts. This is, maybe some drop will be there, but approximately you can say -10 volts. -10 is obviously lower. This is lower. This 0 is obviously higher than any of the negative number. This is P, this is N. P to higher, N to lower. Current will definitely flow over here. If you look at D, this is 5 volts. This is 5 volts. This is 10 volts. 10 volts. This is obviously higher. this is obviously lower. This is P type, this is N type, P to high, N to low. So obviously current can flow. But in this case, you will notice one interesting thing. This is 0 volts, this is 5 volts like thing. This is lower, this is higher, this is P type, this is N type. That's the problem. It will not allow the current to flow. P to high, N to low, then only current will flow. This is wrong. Very nice. Oh my God, we are now coming close to the applications. We are coming close to the applications, guys. Ready for checking out the applications? Well, the first application is this 3-terminal device, which we are going to see in a bit, that is called as a transistor. Another thing is logic gates. That's also what we are going to see now. Also, we are going to see different applications like photodiodes. You will also see, solar cells and all these things. You will see semiconductors are being used. We'll see all these things one by one. But this characteristic graph is so important. It's so important that you will see different applications based just on this graph. Just knowing the current and voltage, there are different things that you can apply. The first thing where did it go? Yes, is basically of a PN junction diode. So the first application, remember a diode symbol was normally a triangle with this as the P side, this as the N side. Look at this, P, this is N. So the first application is LED. You might have heard about LED mobile screens, LED mobile screens or LED TVs. What is this LED? It stands for light emitting diode. It emits light. You will be like, wow, sir, how does it look? It looks something like this. But in your TV, this is even smaller. Even smaller. There is a small PN junction. And we know what happens in a PN junction. The electrons jump from one side to the other side. Do you remember atomic structure, guys? What happens when electrons jump from one energy state to another energy state? From one energy state to another energy state? If they go from high energy to low energy, what happens? What comes out? Light. Yes, photons come out, right? Exactly, that's the same thing which is going to happen in a light emitting diode. So when the electrons go from one side to the other side, you will see they go from high energy to low energy. That creates the emission of photons. So high energy to low energy, the electron jumps. So that is going to, this is your electron. So that is going to create basically light. So you can also say E1 minus E2 is equal to HF, which is the energy of the photon. If you change the energy difference, you can change the frequency. If you change the frequency, you can change the wavelength, you can change the color. So this frequency decides the color of the LED. So if you are ever wondering how do you get blue color, white color, red color, yellow color LEDs, what they do is they change the energy difference, because of which the photon's frequency changes or the color changes. That's how a LED works. A LED is always used in forward bias or reverse bias. Come on guys, answer this question in the chat box. A LED will be used in forward or reverse. Let's see how many of you can get the answer quickly. Obviously LED should consume the electricity. It should allow the passage of current. Only then the electrons will flow from higher to lower energy. Obviously it is used in forward bias. What is it used in? Forward bias. Keep this in mind. Next thing is photodiode. Oh, by the way, I forgot to tell you the symbol of LED. The symbol of LED looks like this. You just put the triangle. Okay, this is your P side, this is your N side. Current will only go like this, forward bias, right? But you show two arrow marks coming out of it. What is those arrow marks? That is the light coming out of it. That's the symbol of a LED. The exact reverse is a photodiode. What it does is it takes in the light, senses it and converts it into current, which you can later identify to find out how much light was falling onto it. Have you ever seen in nice hotels where you go to wash your hands, automatically the tap opens or the water falls from the tap? Have you seen those automatic washing machines? Wash basins? There you will have a photodiode. What happens is basically there is a light over there, or there is a sensor of light, and when you put your hand in the path of that light, the light does not fall on the sensor, it obstructs, that triggers the electrical circuit, and that's when it opens, that mechanism opens up the valve and the tap is open and the water comes out. So there they use photodiode. You might have also seen these days in the cars, there is suddenly these lights which turn on, they are also called as automatic headlamps. As soon as you are driving, suddenly there is a tunnel. You go inside a tunnel, you don't have to turn on the light. Automatically the lights have turned on. Have you seen that? Yeah, even in sanitizers. So that is one of the beautiful applications of photodiode. It senses light falling onto it. So in fact, the symbol for such a photodiode, is exact opposite of a LED. You will see the arrow marks going this way. But there is a catch in photodiode. Photodiode is always used in the reverse bias. Now I'll be like, what the hell? Why do you use photodiode in reverse bias? The reason for using photodiode in the reverse bias is from the graph, the current versus voltage graph. Like I was telling you, this graph gives you a lot of things where you can apply for different applications. See guys, what happens is when light falls on a basically photodiode, okay, on a photodiode, there is sudden increase in that current, or basically the conductivity changes. Now here what happens in the forward bias is that you will see that the current changes are from this value to that value. It reaches maximum very soon. But in the reverse bias, you have a lot of smaller values of current and it becomes more sensitive to small changes in the light. Here, just imagine if more light falls. Just imagine more light falls. This graph will probably become like this. More light falls, this graph will become like this. More light falls, this graph will become like this. Hardly any changes. But in reverse bias, you put more light. Already there is hardly any current flowing through it. You put more light, you will see the graph will go like this. You apply more light, the graph will go like this. You apply more light, the graph will go like this. So what does it tell you? It tells you that the sensitivity of current is higher in reverse bias than in forward bias. So if you want to measure the current dependence on the light's intensity, better measure it in the reverse bias, because you can see how intense the light is. Here you will be like, oh my god, is it on this line or this line? I don't know. Here okay, it's on this line or this line, because they are clearly different from each other. Is that clear? Everybody with me on this? Yeah, even the brightness sensor, GV, very good, very good. So this diode is basically used in reverse bias. That's only because of the sensitivity of the diode's current towards the light falling on it. Very, very crucial. Cool? So it changes very easily. If the changes are small, then you cannot see it easily. But when the changes are large, then you can find it out very easily. That's the whole logic behind it. The next type of diode. Yes, they give us electrical energy. No, Prem. It's not the same as solar cell. Solar cell is completely different. Solar cell gives you electrical energy. That is completely different. Don't confuse photodiode with a solar cell. Okay, that is different. Okay, here when I say it is connected in reverse bias, that means you are connecting a positive terminal here and negative terminal here. That is the meaning of that. In solar cell, there is no battery connected. It is the battery. It is the battery. Understand that. There is no biasing in solar cell. Do you understand the difference? So photodiode does not give you electrical energy. Photodiode is connected to something. Okay. Next is Zener diode. Okay, next is Zener diode. All right. What is Zener diode? Zener diode makes use of the reverse bias voltages, like I'll show you over here. It in fact uses this region of the reverse bias voltage, where you will see that after the breakdown is achieved, no matter what you do, the voltage does not change. It has become constant. The voltage has become constant. That is the use of Zener diode. You'll be like, sir, okay, fine, I understand the voltage does not increase, but how does it benefit us? I will show that to you. By the way, the symbol of a Zener diode is, you basically twist that line like this and like this. That is basically Zener diode. Without them, that is just a normal diode. You bring it down and bring it up. That is called as a Zener diode. Again, it looks very small. You can hardly make out the difference between a Zener diode and a normal diode. It's very small, looks identical only. Okay, now what is going to happen in a Zener diode is it works in the reverse bias, specifically in the breakdown voltage. And if I show a Zener diode maybe like this, because I'm connecting it in reverse bias, and we know this is P side, this is your N side, I will connect this to the positive terminal, this to the negative terminal, this to the positive terminal, this to the negative terminal, correct? Imagine I tell you the breakdown voltage is example 5 volts. Breakdown voltage is 5 volts. Example. That means after 5 volts in the reverse direction, that's it. It breaks down. It suddenly conducts. The voltage remains constant. You cannot increase the voltage beyond a point. So that is a good thing for me. I'll tell you why. Because I can use it like a voltage regulator. How? Observe. Just imagine this. Just imagine this. If I give 6 volts here, okay, 6 volts here as compared to this, I know the breakdown voltage is 5 volts. No matter what you do across this diode, only 5 volts can be dropped. So you will see only 5 volts will come up on this diode, and the remaining part of the circuit, maybe there is a resistance here, you will see 1 volt being applied over here. Out of the 6, 5 comes here, 1 comes here. If by chance you make that 7 volts, this will still remain 5, 2 volts will come over here. If you make that, let's say for example 20 volts, you will see out of the 20, 15 volts will come on the other parts of the circuit, only 5 volts will come over here. What it means is, if I take out 2 terminals from here, the voltage across this will always be 5 volts. Isn't this like a regulator? It is telling only 5 volts can come out, nothing more, nothing less. So this is acting like a regulator. It is acting like a regulator, guys. So irrespective of the voltages, if voltage is more than that breakdown voltage, you will see that across this I am just going to get the breakdown voltage, which is just going to be constant. So hence it is used for regulating the voltage. Yes, a fixed voltage. So it is called as a voltage regulator. Keep this in mind. Okay, great. Okay, I'll just remove that diagram later on. Don't worry about it. There is another use of diodes. Okay, and that is rectifier. So a lot of new names and new terminologies you are learning, okay guys, today. So you learned about Zener diode, you learned about photodiode, you learned about LED, which is light emitting diode. Another thing is rectifier. Yes, Nick, you can definitely watch my lectures. NT-Abhyas, MTG, PYQ is more than enough to score 150 plus. Yes, definitely. Now, what is a rectifier? You all have used a charger, no? Definitely. You would have seen a charger like this. Okay, I don't have a charger now. Oh yeah, I have. Yeah, but I've seen a charger like this, correct? Great. So, On one side you have AC where you put it in the plug point, but your mobile, your laptop or whatever device you are using, that is on DC. AC is there, DC is there. AC is alternating current, sometimes this way, alternating current. DC, direct current, current only flows in one direction. How do you convert a current which is going in both ways to one way, two-way to one-way? So that device which converts two-way to one-way is called as rectifier. Exactly. So what is rectifier? Rectifier is nothing but a device which converts AC into DC. That's all. Now there are multiple types of rectifiers. Let's understand two major types. First one is called half wave. The second one is called full wave. What is the meaning of half wave and full wave? It's exactly what you can imagine only. In an AC signal, you have the positive cycle, you have the negative cycle. You have the positive cycle, you have the negative cycle. That means current flows this way, current flows that way. Current flows this way, current flows that way. In half wave, you only rectify, meaning convert AC into DC, only half of the wave. The remaining half, you just shoot away. It's like saying cars are coming from this side, cars are coming from that side. You make both the cars go in that road, that is full wave. You say no, only the cars coming from this way can go that way, that is half wave. Remaining half of the cars, you're like, show off, get lost, I don't care. So that is half wave. So in half wave, you can see if AC signal has positive cycle, negative cycle, positive cycle, negative cycle, you will see the output will only have the positive cycles, the negative cycles will just go away. But in full wave, I'll explain you the working, don't worry about it. But in case of full wave rectifier, you will see the positive cycle, negative cycle, positive cycle, negative cycle, the entire thing is converted into unidirectional current or DC current. So traffic was going this way also, that way also, this way also, that way also. You now made it only this way. Only one way it can go, it cannot go the other way. So you have converted the entire wave into a DC signal. That's why it's called full wave rectifier. Is that okay, my dear students? Now how does it work? Great, great. Thank you, Moonlight, so much. See this. This is a transformer, okay? Don't worry about it. Transformer is just going to step down the voltage, that's all. Forget this. There is only one diode needed, that's all. In the positive cycle, what is going to happen? In the positive cycle, this diode is going to be forward bias because this is your positive cycle. So this is P type, this is N type. P is connected to positive, N is connected to the lower voltage. It's forward bias, it will allow current. So if whatever current is flowing here will flow through the diode, and if you have some resistance, obviously I into R will give you the voltage across it. So definitely there will be some voltage which is created because of the current flowing through it. There is some current flowing through it. It is allowed in forward bias. But the moment you go to the negative cycle, that means now the current is flowing the other way. This is positive, this is negative. You can see in this diode, this is P, this is N. P is connected to minus, N is connected to plus. This is obviously reverse bias. Reverse bias. Obviously no current will flow. There is no current, no voltage. So only when current is flowing this way, it will allow the output. When current is flowing the opposite way, it will just shoo it away. That's how it gets rectified. You can see that this is unidirectional current. I know it is not your favorite constant current. That's okay, but at least it is flowing only in one direction. That's why it is half wave rectification. I've explained the working through this diagram also, which will be available to you in the slides. Okay, you can see the complete AC signal, only half of the signal is coming out. Half of the signal is coming out. Rest half is just shooed away. Okay, observe this. Okay, input also DC. No, input will be AC, bacha. Look at this. This is AC. this is nothing but AC. This is nothing but AC signal. This is nothing but DC signal. This is AC, this is DC, because it is only flowing in one direction. All right. Now there is another type of rectifier, like I was telling you, full wave rectifier. Usually for these kind of rectifiers, you need 3 terminal transformers. They are called as the center tap transformer. Center tap transformer. So in these transformers, basically there are 3 terminals. Usually there are 2 wires coming, but here you take out 1 more wire from the between. So because of that, what happens, you can get a full wave rectification. How? I'll tell you. You need 2 diodes also. So you need 2 diodes, one diode this way, another diode this way. So it's basically saying cars are coming from here also, cars are coming from here also. There is one traffic police to tell, okay, you guys are coming from here, okay, go carefully there. Another diode, another traffic police asking these cars coming from the other way, okay, listen, you turn like this and go there. So both the cars will eventually go in the same direction. That's the job of the 2 diodes here. So observe what is happening, my dear students, again. Okay, so when you are in the positive half cycle, this is relatively positive, okay, as compared to this side. This is positive, this is, let's say, 0, this is negative. This is relative scale. If this is minus 5 volts, this is 0, this is plus 5 volts. So this diode becomes forward bias, because this is P side, this is N side. P is connected to positive. This diode will become reverse bias, because the P is connected to negative. So this will not conduct, this will conduct. So the current will flow from here to here to here to here. So do you see, through this resistor, current is going from right side to left side? Current is going from right side to left side. Okay, so that current will definitely come out over here. Everyone? Cool? Next, when you talk about the negative half cycle, then what happens? This becomes minus, this is 0 only, this becomes plus. Plus is connected to P, so now this becomes forward bias, and negative is connected to P, so this becomes reverse bias. This becomes reverse bias. So now this will not allow current, this will allow current. So the current will flow from here, because this is forward bias. It will go like this, it will go like this, it will go like this, it will come out like this. Do you see, whether positive cycle or negative cycle, through this guy, the current is only flowing in the same direction, not like this and then like this and like this. No, it's always flowing in the same direction. So that's why you see the current flows in the same direction. Yeah, it increases and decreases, that's fine, but it always goes in the same direction. That's why it's called as full wave rectification. Okay, everybody with me? AC to DC, it's like modulus function. You're taking this guy on the top, you just bend it on the top, that's all. Cool, shall we do some questions? Shall we do some questions? Here comes the question. Okay, a Zener diode having a breakdown voltage, this is a Zener diode, breakdown voltage 15 volts, connected to 20 volts across 250 ohms and 1 kilo ohm. Question is, what is the voltage across 250 ohms? Come on, let's see how many of you can do this. Very direct question. I want everybody spamming the answer in the chat box. Everybody spamming the answer in the chat box. Come on, my dear students. Figure this out quickly. B, sure. D. The answer is D, guys. I'll tell you why. Okay. See this. See this. This is a Zener diode, and a Zener diode operates in reverse bias, and the voltage is basically constant. It is 15 volts. That is basically your breakdown. No matter what you do, this is always going to be constant, even if this is 20. So if this voltage is 15 volts, the total voltage is 20 volts, which is the sum of voltage across 250, there is some drop here, plus voltage across the Zener diode, across Zener it is 15, Across Zener it is 15. Across 250 ohms, how much will it be? How much will it be? Obviously 5 volts, right? So that is why the answer is 5 volts. Everybody got it? So the total voltage was 20. 5 here, 15 here, 5 plus 15, 20. That's all. Great. Now I am thinking of one thing. Okay, instead of overloading you, I will take a separate class on transistor, or maybe I'll just try to make a very conceptual short video for transistors which you can understand maybe in 15 minutes or something. Okay? Instead, what we'll do is we'll do logic gates, because logic gates you will enjoy also and you will learn it through live session easily rather than transistor. What say guys? Let's do that. Okay, so probably let me just go to logic gates quickly. Just 1 second. Don't worry. Okay, I'll go to logic gates now. Okay, so let's understand logic gates, because you're going to enjoy this to the core, and guarantee I've seen many times they ask questions from semiconductors from logic gates. Even last year, if you see, there was a question in logic gates. So 4 marks are there in your pocket. Now, have you used the regulator of your fan to try to increase the speed of the fan? You turn it like this, like this. The speed of the fan increases or decreases. What is it changing? Basically, it's changing the current or the voltage, right? Of the fan, correct? It's changing the voltage or the current of the fan, right? Very good. Sometimes you might have seen some fancy hotels or some fancy systems. They have something like a press touch to button. Yeah? You press that button, tuck, tink, tink, some noise will come and it shows some digits, 25, 50, or you can change the temperature like that on, like in your AC remote, like the one I have here, right? You can change. You press this button, you see some values over there and something happens, the speed changes. You can increase it in steps. So that's exactly what is the difference between analog and digital signal. In analog, you can get any value of voltage or current that you want. You can just turn it around. You can just just like pressing the accelerator of your car or your bike, you can accelerate it how much ever you want. But if I tell you, no, listen, I'm going to give you switches over there, or I'm going to keep some buttons or some kind of, buttons like this. You press this, your speed will go to 5 kilometers. Then you press this again, 10. You press it again, 20. You will not be so happy about it, 100%. Like, what is this, sir? I can only go 5, 10, 15, 20. I don't like this. But that is digital signal. Okay, that's a very crude way of explaining what is digital signals. Okay, so they are just like this or that or this or that. But in analog, you can get whatever values that you want. Yep. Now, you will be like, sir, so digital is bad. But that's the beauty of digital signal. Digital signal is not going to be affected by some external factors like noise or some loss of voltage or some external factors which change the current, drop in the voltage or drop in the current because of the resistance. Here it is either high voltage or low voltage, more voltage or less voltage. You understand only this or that. There is nothing in between. There is nothing in between. That creates more clarity and it reduces the noise. Like if somebody tells you, will you come out for this party? That person says, yeah, listen, I will do one thing. I will see if I can go there and then I will pick up that. I will drop that person and I will see if I can come like that. I don't know. Be like, are you coming or not coming? You just tell me that. So digital signal is like that. It's like a clarity. 0 or 1, true or false, yes or no, high or low, 5 volts or 0 volts. Analog, so many shades of gray. So many shades of gray. This is also possible, that is also, that this, so many values are possible. And our computers, our mobiles, our AC remotes, this remote which I use, it understands not analog, digital signals. 0, 1, 0, 1, 0, 1. And you might have heard or you might have seen in fancy movies, some programmer is programming, or in some animation, 0, 1, 0, 1, 0, 1, 0, 1, everywhere on the back of the screen. What are these 0, 1s? These are the only things that these stupid machines can understand. That's all. They don't understand anything else apart from yes or no. Yeah, even clocks, digital clocks, nothing else they understand. True or false, 1 or 0, all of them mean the same thing. High, low, on, off, yes, no, high, low, 0, 1, on, off, all are the same thing. Many circuits are digital. You will be like, sir, this is crazy. I mean, how can just 0, 1 decide so many things around us? But that's the beauty. It can. And the way you interpret these 0 and 1s can change the definition, can make you transmit so many messages, it can mean so many things, the pattern in which you send these 0s and 1s. And that's how everything around us works, be it computers, remotes, whatever. But to do that, you need a logic. If this is happening and this is happening, then turn this on. If that is happening, that is high, that is low, then do this. If this is off, this is on, then do that. There is logic inside your processors. You take anything like this or the remote, you will see a small circuit inside your phone, tablet, TV, whatever. Have you seen that? Yes or no? All of them have logical processors. There are processors, these have some logic in it. So they work only under certain conditions. When these conditions are met, then it will give this. When these conditions are met, then that will happen. Ifs and buts, ands and ors, no's and yeses, that's what is there inside these chips. It's a brilliant brain of all the devices around you. And it's not so simple to explain also that what is exactly the logic of this entire chip, sir. It's a combination of lots and lots of ifs and buts. But at the basic level, there are only 3 major operations which are happening. Or, and, not. Or, and, not. That's it. These 3 logical operators can build up the entire logical system of your chips. You'll be like, wow, that's great. That's cool. Or, and, not. Or, exactly the same word in English, and, just like you use it in English, not means no. What do they mean? I'll come to that, but before that, let me tell you the smallest building block of any chip or any logical circuit is called as a logic gate. It is called logic gate. What is it called? Logic gate. It will have some inputs, it will have some output, it will have some input. So that input will see, oh, this is high, this is low, so output should be low. Oh, this is true, that is true, then this should be false. Okay, this is 0, oh, this should be 1. So it's called as a logic gate. It's like a gate. This, that, then this. There is a condition to that. So first is a OR gate. So OR means if this is true or this is true, then the entire thing is true. I'll give you a best example of that. Okay, just come up over here. Yes. Imagine, oh, by the way, you need something called as the truth table for all these gates, which gives you a certain set of conditions. If this is there, then what should happen? If this is there, then what should happen? That is called as the truth table. So let me just show that to you. Here you have the inputs and here you have the output. This is called as my truth table. Truth table. Champa decides that she will marry Pandu if Pandu is rich or intelligent. What did Champa decide? Put it up in the chat box so that everybody can read. Let's see if you are hearing properly. Champa decided she will marry Pandu if he is rich or intelligent. If he is rich or intelligent. Let's see what is the output. Let's see what's Champa's output going to be. Crazy, rich or intelligent. She finds Pandu is rich. Pandu is also intelligent. Very good. Champa will get married. Yes or no? Champa will get married. She sees Pandu is very rich, but he is not intelligent. Okay, he is rich now. Fine. True. True, false, true. Pandu is not rich, but Pandu is intelligent. Okay, no problem. Pandu is not rich, Pandu is not intelligent, she will not get married. That's what is the truth table. Understood? This is what a truth table looks like. You can also put 1, 1, 1, 0, 0, 1, 0, 0, or you can put true, 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 false, false, true, false, false. Whichever you want. Or high, low, on, off, whatever. All of them mean the same thing. This is the Kundali. This is basically what Champa is going to see. Rich, intelligent, whatever. Example. How do you show it in expression? You put a plus mathematically. This is your truth table. 0, 0 gives 0. Both are false, false. Either one of them is true, then it is true. Any one of them is true, it's true. Diagram wise, symbol wise, you put a D-shaped symbol, but you curve this, that is called as an OR gate. This is one of the input, this is another input, this is your output. You give 0 here, you will get 0 out. You give 0 here, 1 here, you will get 1 on the other side. The plus means OR. The plus over here is OR. So guys, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is not 2, it is 1. Be careful. What is 1 plus 1? What is 1 plus 1? It is 1. Because here plus is not that plus. Plus means OR. Plus means OR. Okay? Yep. Very good. Very good. Excellent. Next is AND. Champa says, I will marry Pandu only if Pandu is rich and intelligent. My goodness. So let's see what the table is going to look like. Rich and intelligent. Let's see what the output is going to look like. She sees Pandu is rich and intelligent. She will get married. She says Pandu is rich but not intelligent. Here the word used is and. Both he should be. Nope. Pandu is not rich. Pandu is intelligent. No use. Pandu is not rich nor intelligent. No use. Gone. Understoodo? Clearo? This is the truth table for AND gate. And a logical gate. Here the symbol used is dot. Very good, Anger Queen. Yes, these are like PNN. The symbol for that is a proper D. If you bend it, it becomes OR. If you keep it straight, it is AND. This is very easy to remember. AND has the D, na? The D looks like this. So AND gate. The symbol is dot. So just to give you mathematical expressions, 0.0 is 0. 0.0 is 0. 0.1 is 0. 1.0 is 0. 1.1 is 1. Exactly what the truth table tells me. Perfect. Next is NOT gate. Next is NOT gate. I mean, just imagine this. What will NOT gate be? It's like, you know, exactly whatever is there, opposite of that. Imagine, Champa says, let's say she sees if Pandu is rich. If Pandu is rich, okay, this is the output. She sees that if Pandu is rich, I will not marry. If Pandu is not rich, then I will marry. Exactly opposite. She's checking something, or you're checking something. If that is true, then the outcome is false. If that is false, the outcome is true. If this is off, that is on. This is on, this is off. Exactly opposite. That is called as a NOT gate. Exactly negation. The symbol for that is just a triangle with this dot. Yeah, it looks like a diode. It looks like a diode, but it is not a diode. There is a dot over here. Okay, please understand, in a diode you have that bar. There is no dot. Okay, so don't get confused between a diode and this. Okay, great. So this NOT gate exactly negates. The symbol for that is a bar. You put a bar over on the top. You can see the truth table, 0 gives 1, 1 gives 0. So if I say 0 bar, it will be 1. If I put 1 bar, it will be 0. If I put 0 bar bar, what is the answer? 0 bar bar. What does the dot mean? Dot means, it's not like multiplication. You can think of it like AND, like I showed you over here. The dot means AND. Symbolically, AND means that dot. Okay. Plus means OR. So what does the bar mean? Not. 0 bar bar means 0 bar is 1, 1 bar is, so this will just become 1 bar, which is again becoming 0. 1 bar bar bar, 1 bar bar bar, 1 bar bar bar. Is it not like 1 bar? Is it not going to be 0? Very good. Excellent. Got it. Perfecto. Now, there is something more what you should know, that is called as NAND and NOR. NAND and NOR are also additional gates. You can use these NAND and NOR gates and make any other gates. In fact, they are also called as universal gates. Let me tell you what NAND is. NAND is NOT and with NOT is NAND. So NAND gate is nothing but you take a AND gate and put a NOT gate in front of it. So it is AND with a NOT. That's why you see a dot over here. Do you see that? There is a dot. That dot was not there in case of a simple AND gate. That is not there. That is a simple AND gate. But when you put a dot, the moment you put a dot, it is a NOT gate. Basically, what is it? NAND gate. Okay. Now, what is a NAND gate going to do? If you are expecting 1, you will get 0. If you are expecting 0, you will get 1. Look at this. 0 and 0, 0, right? But the output will be 1. Because it's a NAND gate. 0 and 1 should have been 0. 0 and 1 should have been 0, but the output you will get is 1 because it is negating it. 1 and 0, you should have got 0, but you are getting 1. 1 and 1, you should have got 1, you are getting 0. It's exactly negating it. So A dot B is AND A and B, the NOT of it. So that's why you put a bar. Dot signifies AND, you put a bar, it becomes a NOT. Got it, guys? Everybody understood this concept? How these gates are working? Similarly, can you tell me what is NOR gate? What plus what is NOR? Put it up in the chat box. What plus what is a NOR gate? Which logic plus which logic is a NOR gate? Obviously, it is going to be an OR gate plus a NOT gate. OR plus a NOT gate will give you a NOR gate. So this is actually A or B, the NOT of it, the NOT of the negation of A or B. Think 0 or 0, rich or intelligent. Okay, both are false, false. But what you will get is exactly opposite. False, true, true, but opposite. You will get false. True or false is false. Or you will get true or false is true. So you will get opposite, which is false. True or true should be true, but what you will get is a false over here. Is that okay? That's how it works. Very good. OR and NOT. Awesome, guys. Now, before going ahead, let me give you two important theorems which will help and save your life, and those are called as De Morgan's theorem, it is nothing but A dot B bar is equal to A bar plus B bar. Very simple. A dot B means A and B. So the knot of A and B is basically the knot of A or the knot of B. That is what it is. The other statement is A plus B bar is A bar dot B bar. Oh, sorry. My bad. I have to put it. Yeah, correct. Fine. It's fine. Yes. So A plus B whole bar is, separate them out, but put, instead of plus, you put the dot. That's it. So this is basically the knot of A or B is equal to the knot of A or the knot of B. This theorem will help you at times, depends, but I'm just giving it to you. Okay, these are called as the De Morgan's theorem. This is called as a basic algebra. Let's see if you guys can solve this. There are some signals. You can see it's 0, suddenly it becomes 1 or high. There is low, it's high, it's low, it's high. This is the output. These two are the inputs. This is the output. Looking at the inputs and the outputs, can you guess which gate it is? Which gate it is? Last two questions, guys, then we are completing the syllabus. More 2 minutes, 3 minutes. Come on, figure this out. This is 0. Observe carefully. This is low. This is low voltage. So 0 or off or false or no. This is also low voltage. Output is also low. Correct? Okay. This is 0. This is 1. This is 0. This is 1. This is 0. Low. The output is 0. This is high. This is high. This is high. Acha. 0 and 0, 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. Acha, this should be AND gate. This should be AND gate. Very good. Very good. Very good. That's the correct answer. Perfecto. Understood, guys? This is like an AND gate. Why is it an AND gate? You can put up the truth table. 0, 0 gives 0. 0, 0, sorry. 0 and 1. 0 and 1 gives you 0. 1 and 0 gives you 0. 1 and 1 gives you, 1 and 1 gives you 1. So this is the truth table for obviously AND gate. Is that clear? Perfect. Moving on to the next question. There is some logical circuit written over here. Can you figure out what will be the best way to represent this logical circuit? Best way to represent this logical circuit in the algebraic mathematical form? Go step by step. Name each of the gates, you will get it, guys. This is basically AND gate. This is basically NOT gate. This is basically OR gate. This is basically NOT gate. 3 inputs are there, huh? 3 inputs are there. Look at this. This is B. So what will this point be? This will be B bar, right? This is B. This is negating B. So this is B bar. This is ANDing it. So at this point, what should you get? At this point, what should you get? B bar and this C. Because this C is coming as an input. So AND C, that means B bar dot C. Correct? Very good. The same input is going over here also. Next, this A is going as it is over here. This point is just nothing but exactly this B bar dot C. Sorry, not C bar, B bar dot C. Correct? Everybody sees that? So what will be the output of this? You have to OR this. A or this thing. B bar dot C. OR means plus. So A plus B bar dot C. That is what you are getting over here. What will the final output be? What will be the final output? Basically not of this. That means A plus B bar dot C not. That means you put a bar over all of them. All of them. Where is it? Where is it? Option D, right? Option D. Can you see that? Very nice. This is how you have to think. These are logical gates. It's not that difficult. I have kept some homework questions for all of you. I'm assuming and expecting that you will mark your attendance by putting up the answers in the comment section, even if it is wrong, or else I will not know and I will not get the motivation to conduct these classes. Okay, I've come here to make sure that you guys learn. You have to show that interest. You have to reciprocate. It's a two-way relationship. Remember that. Just second. Oh, forget the transistor question. Okay, then this one also you are going to solve. Okay, make sure you solve the question and put it up in the comment section. And this is also another question on logic gates. Solve these questions. Answers will be coming up on the Telegram channel, of course, and I will be giving you the transistor related theory in a separate file, and then we'll be having a combined session of problem solving, okay, in the days to come. So make sure you check out also the crash course, which is there in the description box. Do not forget to leave the comments, mark your attendance by putting up the answers, okay? All right, bye bye guys, have a great time. I hope you enjoyed and learned a lot. You had fun too. Keep learning like this, keep reciprocating, get in all your friends, get in all your batchmates on the channel, because me and Wazim sir are ready to rock on, and we are going to make sure that you guys excel in NEET 2023. That's a promise to us, a promise to you. Okay, bye bye, have a great time. Hasta la vista, take care.